Let's now try to make some connections between standard deviation, z-scores, and the empirical rule. So I'm going to use the same example that we've looked at before. On the left-hand side here, I've got the actual frequency distribution for the daily maximum temperatures in San Francisco, and I wrote down the value of the frequency bars throughout the distribution. Recall that we said that these daily maximum temperatures are approximately normal. Again, I know that the data doesn't fit that bell-shaped curve perfectly, but again, we're approximating with the normal distribution, which tells us that at the center, we can expect the mean value to be at the center. So for San Francisco, that mean value was 65 degrees. So on average, the temperature in San Francisco is about 65 degrees Fahrenheit. And the daily temperatures vary by about 8 degrees Fahrenheit. So that's the sample standard deviation. So using this idea that daily maximum temperatures are approximately normal, on the right-hand side here, you can see that I've drawn a bell-shaped curve to represent the daily maximum temperatures. And then I went ahead and wrote out the temperatures that are 1, 2, and 3 standard deviations away from the center. So those are those values that I just boxed in blue. Right below them, we can see the corresponding z-scores for those temperatures. So in red here, these z-scores tell us how many standard deviations away each of those temperatures are. So for example, 81 degrees Fahrenheit means that 81 degrees Fahrenheit has a z-score of 2, telling us that 81 degrees is 2 standard deviations above the mean. So a z-score basically just tells us how many standard deviations away from the mean a particular value is. Okay, so now let's use the empirical rule. And remember, the empirical rule says that values that are 2 or more standard deviations away from the mean, so I box this in green, values that are 2 or more standard deviations, so it could be above the mean or below the mean. So that means temperatures that are less than 49 degrees and temperatures that are greater than 81 degrees are going to be our significantly high and low values. So in question A, what temperatures are significantly high? We can see that temperatures that are, temperatures that are 81 degrees Fahrenheit or higher are going to be those that are significantly high. And we can say because, all right, these temperatures have z-scores that are 2 or more standard deviations above the mean. Okay. And if we take a look at the shaded area that marks 81 degrees and higher, all right, according to the empirical rule, we expect that only about 2.5% of data values are going to be above 81 degrees. Okay. What temperatures are significantly low? So same idea, using the empirical rule, those are going to be temperatures that are that have z-scores of -2 or smaller. Okay, so this means that temperatures of 49 degrees Fahrenheit or lower would be significantly low. And again, same reasoning, but here we would say because these temperatures have z-scores, okay, that are 2 or more standard deviations, okay, below the mean, okay. All right, and again, according to the empirical rule, we expect that approximately 2.5% of our daily value or daily temperatures are going to be less than 49 degrees. But I actually want to use the frequency distribution on the left here to approximate the actual percentage. Looking at the frequency distribution on the left here, I'm going to mark where 81 degrees is. So here, that's approximately 82.5. So 81 degrees is going to be in this frequency bar here. It's going to be in that class. So if we are trying to estimate approximately how many days do temperatures, how many days out of 365 days, are temperatures in San Francisco higher than, so that marking is 81 degrees Fahrenheit, higher than 81 degrees. That means we're going to count up this frequency bar that I just shaded in red and the frequency bar above it. So we would add those days. That's 15 days plus 10 days plus 5 days. So let me just do the math off to the side here. 15 days plus 10 days plus 5 days where temperatures are higher than 81 degrees Fahrenheit. That's out of 365 days. So that gives us a probability or a proportion of approximately 0.082 or 8.2%. So we expect that approximately 8.2%, so here that's 8.2% of daily maximum temperatures are going to be 2 or more standard deviations above the mean. And so we can also see here that this kind of contradicts that rule of thumb that we use for determining significantly high and significantly low values. According to the empirical rule, values that are 2 or more standard deviations away occur at a probability that is 5% or less. And here we can see that 8.5% is slightly higher than 5%, okay? But it's not that much higher. Okay, let's take a look at question B. So those temperatures that are significantly low. So again, let me just mark on the graph here. This marking here is about 52.5 degrees. And so according to the empirical rule here, we can see that temperatures that are 49 degrees or less are 2 standard deviations below the mean. So that means that those temperatures are in that first frequency bar, which is 10. So let's do the calculation here. That's 10 out of 365 days, which is approximately 0.027 or 2.7%. So approximately 2.7% of the daily maximum temperatures in San Francisco are less than 49 degrees. So here, this does this does match up with that criterion. It is less than 5%, so it makes sense that that checks out there. Okay, the last part here, question C, I want us to take a look at how do we work backwards to actually find the temperature value that corresponds to a standard deviation of 1.5 above the mean. So here, this is where you need to use that formula for a z-score, but we're going to work it backwards. So up at the top here, because I'm kind of running out of space here, I'm going to write down the formula for calculating a z-score. So that z-score relates the data value of interest. So we subtract it from, since we have sample data here, I'm going to use the sample mean value x bar over the sample standard deviation. So here we're going to take this formula and we're going to solve it for x. So using some algebra here, I'm going to multiply both sides by s, and that gives me this equation, and then I'm going to add x bar to both sides. So this tells me that x is equal to z times the standard deviation plus the sample mean. So we can use this formula to find any value when we know that value's z-score and we know the mean and the standard deviation for the sample. And we can also do this for the population as well. So here, using that formula for the z-score and solving for x, I'm going to write that formula down again. You can just memorize this formula. And again, if you had population data, let me just give you that equation. We would use sigma instead of s, and then we would add mu instead of x bar. Okay, so substituting everything that we have, x represents the temperature. So we want to know what temperature corresponds to 1.5 standard deviations above the mean, so that's the z-score, for this sample data that has a sample standard deviation of 8 degrees Fahrenheit and a mean of 65 degrees Fahrenheit. If you do that calculation, 1.5 times 8, that gives us 12. 12 plus 65 gives us 77 degrees Fahrenheit. So this is telling us that a temperature of 77 degrees Fahrenheit has a is 1.5 standard deviations above the mean. And if we go back to this bell-shaped curve on the right here, I'm going to use yellow here. No, it might be hard to see, but we can see that it makes sense that this answer is correct because 77% is between 73 and 81, and then we can see that that is between 1 and 2, so 1.5 is somewhere in between, okay?